So today we are going to be having a look at angles, and more specifically when you have angles in a straight line, angles in between parallel lines, angles in your triangles and quadrilaterals and stuff like that. So I'm going to start with a little bit of theory, and then what we're going to be doing is we are then going to go to GeoGebra, my favorite program, and actually see it in practice. So let's just deal with a bit of basics. So your angles with lines. All of this is in your notes, and I will tell you exactly where it is. It is week 13. Week 13. Yeah, should be week 13. No, that's the introduction. Week 20 is when I get into it properly. So week 20 is lesson 62, 63, and lesson 64. All right. So lessons with angles, you know that that is a straight angle, and that if it is two arms on either side, that this angle over there is 180 degrees. Which means that if I draw a line in there, and let's use a different color, so let's use blue, for example. So if I draw a line over there, and this one, for example, is 60 degrees, because the whole thing is 180 degrees, I know automatically that this must be 120 degrees, so that the whole thing adds up to 180 degrees. And this is known as lines. It's not known as lines. It is known as angles on a straight line. You then also have vertically opposite angles. Vertically opposite angles happen when you have some version of a cross shape. Then you'll know that this angle here, again, let me just get a different color so we can differentiate. This angle over there is going to equal this angle over there. Now, how do we know that? Well, if I know, for example, that this is 60 degrees, and I use this straight line, if that's 60, that must be 120. But if we use this straight line, and that's 60, that must be 120. Therefore, they will always be equal. And if that's 120 and that's a straight line, we know that is 60, which means both sides of my vertically opposite angles work. All right. You also know that if you measure the angle all the way around a point, this will be 360 degrees. And these sort of things are small ideas, but they actually play quite a big understanding in when we come to triangles and quadrilaterals, and when we look at the total summing of those angles, why they're actually equal to what they do. So I am going to also have a look at just particular names of angles. So you know that if you have an angle like this, where this is somewhere from 0 to 90, but not including 90. So just for ease sake, I'm going to say 89. And essentially, if you have 0, it's not an angle. So let's say 1. Please note, I am just going on whole numbers. I do agree it could be 89.5, 89.9, but you get the idea that it's somewhere between like 1 and 89, just below 90. These are my acute angles. You have that when you have this kind of angular bit there, like a box. That is my right angle. And my right angle is 90 degrees. If it's larger than 90, but smaller than 180, that is my obtuse angle. And then if we have a bit of a backwards turn, so we have this angle here. So that is over 180 to just under 360. That is known as a reflex angle. And then your full 360 is a full revolution. So I'm pretty sure all of you guys know this. So when we come to triangles and other angles, to prove that, for example, all the angles in a triangle add up to 180 degrees, we need a little bit more, and that's to do with parallel lines. So what are parallel lines? Well, we denote parallel lines by these angles, not angles, arrows. So they have arrows on the lines, and the symbol for parallel is actually that, which is two parallel lines. So what are parallel lines? They essentially are lines that never touch. They are lines that have the same slope or same gradient. So they just keep on going, and the distance between them will always remain the same. Okay. Now, what about if we have another line that crosses them? So let's say there's another line. So the line that crosses my parallel lines is known as a transversal. Big name. If you know it or not, it doesn't really matter. You won't be asked, please name this, but they may mention this word in a question, and at least then you know what they're talking about. So then we have created some angles around here. Because if we just look, for example, over there, this is kind of like that X shape with a vertically opposite that I was telling you about. So I will know that this angle over there, let me mark that a little bit better. This angle over there will equal that one over there, and this angle over there will equal this angle over there. Okay. But if these lines are parallel, they have the same direction, the same slope or gradient. I wonder if there's a way that we could relate these angles to these angles. And it turns out that we can, in that they're actually exactly the same. And that's why I'm doing it in the same color, where that equals that, and that equals that. And more importantly, I've used the same symbols because these angles are actually equal to each other. Because the way that this transversal cuts this one line is the exact same way that it cuts this line, because these two lines are essentially equivalent lines, just in a different place. So that opens up quite an interesting idea here. And there are three kinds of parallel line angles we are going to be having a look at. And I am going to deal with this in, let's do purple to start. So the fact that this angle here and this angle here are equal, this is known as corresponding angles. And with corresponding angles, they are on the same side of my parallel lines and its same side of transversal. So we notice this angle is above my blue parallel lines in both of them, and it's also on the right of my transversal. So we can do this with a whole bunch of angles. So if we take that one and that one, they are also corresponding. This one and this one are corresponding, this one and this one are corresponding. So this is generally known as the F of parallel line angles. And that is because you can actually create an F shape. So let me make this a bit clearer. So there's the top of my F there. Here is the vertical part of my F there. And here is the middle horizontal part of my F there. And the angles are on the inside of my F. So essentially it is over there and it's over there where these are my parallel lines. So those are known as corresponding angles. Okay, that's quite useful to know. So that is number 1 of 3. So let's get rid of some purple here. So there's purple going. No. Purple. And then all of this stuff can go, which is great. All right. Then we have another guy. And this guy I am going to do in black. And draw. So we have alternate angles. So alternate angles are when you have an angle here and an angle here. So it is essentially the opposites. So remember, corresponding angles, same side of the transversal and same side of parallel lines. Alternate angles is opposite sides of the parallel lines, opposite sides of the transversal. All right, so opposite sides of parallel lines and opposite sides of transversal. And these angles are generally known as the Z angles or the N angles. So in this scenario, it would be a bit of a Z, where there's my bit of my parallel line. I then go down my diagonal bit, and then I go across. So it's kind of like a stretched out Z. So that Z is kind of pushed together. If you hold the two bits and you stretch it out, you then have a Z that kind of looks like this. All right. You might also notice, if you turn your head to the side, that you could have an N shape that looks like that, going up, down, and up, with the dot over there and the dot over there. So it's totally up to you which way you look at it. That's as well a nicer Z shape, more the type of Z that you've seen before. It's totally up to you. So it's these interior angles over there with those parallel lines, or if my parallel lines are vertical, it's those interior angles over there. So currently we've dealt with an F shape, we've dealt with an N shape, and now we're going to be dealing with a U shape. And that's why these things are known as fun angles generally, because the three kinds spell out fun, the F, U, and the N. All right, so let's get rid of this. And it's interesting to think that we've now dealt with two different kinds of situations. One where we're dealing with the opposites on both, being opposite side of transversal and opposite sides of parallel lines. And the other one is where we deal with the same side of transversal, same side of parallel lines. So now there's only one more option that you can actually deal with. And that is if you have the same side of the one and opposite sides of the other one. All right. And these are known, and I'm going to change color again for consistency. I don't think I actually saved that one. Save, and now redo the elimination. All right. So we want, I'm going to do this one in orange. So this is co-interior angles. So co-interior angles are when they are squeezed to the interior of your parallel lines, but on the same side of your transversal. So same side of transversal and opposite sides of parallel lines. So this, for example, that angle there and this angle here would be co-interior angles because they're on opposite sides of my parallel lines. Top one is on the bottom and bottom one is on the top, but they are both on the right of my transversal. And here you can see they create a kind of a C or a U shape, both on the inside. So here's the C or the U shape, where you have my two angles in there, parallel lines, or on the side as we see it here. There we go. More importantly, though, we've been dealing with equal angles. This one is different. This one has supplementary angles. What are supplementary angles, you may ask? They are angles that add up to 180 degrees. And that should make sense because this angle is a green dot. That angle is a green dot, and we know those two are equal because of corresponding angles. And we know that those two have to add up to 180 degrees because of angles in a straight line. Therefore, these two must add up to 180 degrees as well. All right, co-interior angles is actually beyond the syllabus. However, there's no point in not covering it when it takes exactly the same amount of cognitive ability to understand this compared to the other two. All right, so therefore, if we have a look at your triangles, over here, for example, we can prove that angles in a triangle actually add up to 180 using parallel lines. So there we go. So these are parallel lines. This one just touches the tip there, and this side is extended on either side to be parallel. So this angle here will equal that angle there. Why? Because we've got alternate angles. There's my N or my Z. This angle here must equal that angle there. Again, a backwards Z for my alternate angles. And of course, this angle there will just be there because it's in the triangle already. And I know that these three must add up to 180 degrees because of angles in a triangle, because of angles in a straight line. But that is those three angles, which means that inside, all three angles have to add up to 180 degrees. Very interesting, actually. So a question that came in, can you have three parallel lines? Yes, most definitely you can. Three parallel lines. Transversal through it, and the exact same thing will happen all the way through. So irrespective of how many parallel lines you have, it's exactly the same idea. And if we have quadrilaterals, the interior angles sum to 360 degrees, which also makes sense because if you take two parallel lines, you know that inside here we've got 180 degrees, and inside there is 180 degrees. Now, these two lines will never touch if they're parallel. But if you just squeeze them a hair inwards, eventually at the end they're going to touch, which means that you're going to have a shape that kind of looks like this. And this is a quadrilateral, and I know that a quadrilateral has four sides because quad means four and lateral means side. And the angles that have now been created here, I can now bring into my shape. So if I create parallel lines, I can do the exact same thing. Imagine all of these are parallel. I'll know that this angle there equals that angle there. I'll know that this angle there equals that angle there. I'll know that this angle here equals that angle there. I'll know that, what else can I use? Let's use a square. That angle over there equals that angle over there. And therefore, that angle and this one will just be inside. But that sums to 180, and that sums to 180, which is 360. But those are all the angles inside my shape, meaning that inside a quadrilateral, you have to have 360 degrees, exactly the same way that you prove triangles. All right. So a couple of questions that came through. Does your fun rules apply if it's three lines? Absolutely. You just pick a pair of two, and it could be those two, or the outside two. Doesn't matter. Everything is exactly right. And everything works exactly the same way. And then over here, the question came in, is this a rhombus? It could be. So a rhombus is kind of a skewed square where all the sides are still equal in length. It could be. Or this one might be flattened a little bit less, and this one might be flattened a little bit more. Then it won't quite be a rhombus. It will be more of a bit of a skewed kite, but that sort of qualification you won't need to worry about.